Hello. So far, our discussion on metals was based on the free electron model. The free electron model of metals gives us good insight into the heat capacity, thermal conductivity, electrical conductivity, then the magnetic susceptibility, etc. But this model fails to explain the distinction between metals, semiconductors, and insulators. Okay, so this classification was not explained by the free electron model, and also the concept of positive Hall coefficient also is not explained by the free electron model. In this chapter, we shall see that the electrons in a crystal are arranged in energy bands separated by some region of forbidden region called energy gap or band gap. Okay, so this is the result of the interaction of these free electrons with the ion cores, positive ion cores in the crystal. All crystals contain electrons. The crystals can be classified into insulators, conductors, and semiconductors based on the electrical conductivity of the crystal. The electrical conductivity of the crystals can be explained on the basis of how these electrons can respond in an electric field applied to these crystals. Okay, if there is enough freedom for electrons to move in an electric field, then they are called conductors, and there is no freedom for electrons to move, then they are called insulators. Okay, now let us explain how the classification of this crystal is done on the basis of the band structure of the crystals. Here I have shown the band structure of three different crystals. In the first one, the first band is completely filled with electrons, and the second also filled with electrons. The third one is completely empty. Okay, so since these bands are either filled or empty, no electrons can move in an electric field. So such crystals with either filled or empty bands are called insulators. Okay, so whereas in the second case, the first one is filled, the second is half filled, okay, partly filled, okay, and the final one is empty. But because of this second band, which is partially filled, the electrons can move in an electric field. So these electrons in the second band can move in an electric field. Okay, so they are called conductors, or these are metals. Okay, such crystals are metals. And in some crystals, the first band here, first band is completely filled. The second band is almost filled, but not completely filled. Okay, so such crystals are called, here it is almost filled. So such crystals, there are limited freedom for electrons to move, and these are called semiconductors. Semiconductors. Okay, here the last one is empty, but because of the second band, here the electrons in this band have moderate freedom in an electric field. Okay, so therefore this is called a semiconductor. Their conductivity lies between insulators and metals. And in some semiconductors, very small fraction of the band is filled. Okay, all other part of the band is empty. So such crystals are also called semiconductor crystals. We can understand these band structures if we extend our free electron model to accommodate the periodic potential of the iron core in the crystals. Therefore, the model is called a nearly free electron model. Okay. Now we are going to discuss the nearly free electron model. The band structure of the crystal can be explained by the nearly free electron model. In this model, the band electrons are treated as perturbed only weakly by the periodic potential of the ion cores. The free electrons are moving through this periodic potential of the ions. That means ions are periodic periodically arranged ions, because these are crystals. When the electrons are free, then inside the metal the atoms become ions. Electrons are moving through the fields of these ions. So the potential energy of this interaction will be like this. The electrons are interacting with the positive ions, therefore the potential energy will be negative. So in this axis it is the distance. So, so this potential will become large negative near this ion, and it will be 0, and it will again become negative. So this is the kind of potential through which this electron move inside the metal. Okay, and at the boundary the potential is infinity. So here V is infinity, here negative, therefore there will be attraction with these positive ions. Okay, so this is the nearly free electron model. With this model we can explain the band theory of crystals. The Bragg reflection of electron waves is the cause of this band gap in the crystals. We know that Bragg condition for electron waves is K plus G, or the reciprocal lattice whole square, is equal to K square. Or we can write, we have other expression, K dot 2K dot G is equal to G square. Or we can write K is equal to plus or minus G by 2. But the reciprocal lattice vector G is equal to integral multiple of 2 pi by A. Okay, that means 2 pi by A is the primitive lattice vector in the reciprocal lattice space, when A is the lattice vector in the primitive lattice vector in the real space, and any reciprocal lattice vector will be integral multiple of this unit, okay, in one dimension. Therefore the Bragg reflection occur at K equal to plus or minus n into 2 pi by A divided by 2. Okay, so this is equal to plus or minus n pi by A. Okay, therefore the Bragg reflection, the first Bragg reflection occur at K equal to plus or minus pi by A. Okay, so in reciprocal lattice space, or in K space, this region is called, the region enclosing this is called the first Brillouin zone. Okay, in K space. The next Bragg reflection occur at other values of n. Okay, so K is equal to plus or minus 2 pi by A, plus or minus 3 pi by etc. The wave function at K equal to plus or minus pi by A are not traveling waves. A traveling wave is of the form e raised to I k x, that is, or e raised to I pi by a x, or e raised to minus I pi by a x. Okay, so these are traveling waves. But at k equal to plus or minus pi by a, this is not the wave function. The wave functions are made of equal parts of wave traveling to the right and to the left. Okay, so this is the wave traveling to the right, this is the wave traveling to the left. We can have two waves, that is psi plus is equal to e raised to I pi by a x plus e raised to minus I pi by a x. Okay, so this is one kind of wave, and the other kind of wave is wave function is psi minus, which is given by I pi by a x minus e raised to I pi by a x. So these are the two waves. Here a wave traveling to the right is Bragg reflected and travel to the left, and a wave traveling to the left is Bragg reflected and travel to the right. Okay, so they form a standing wave, not traveling wave. Okay, standing wave means it does not go anywhere, the energy does not carry to anywhere. Okay, The wave functions can also be written as this is equal to e raised to I pi by ax plus e raised to minus I pi by ax. Therefore, this can be written as 2 cos pi by a x, and this is equal to 2i sin pi by a x. Okay. Corresponding probability density of electrons is say plus mod square of this thing, which is equal to, which is proportional to cos square of pi by a x, and this is the probability density corresponding to psi minus is psi rho minus is equal to mod square of psi minus, which is proportional to sin square pi by a x. The probability density of electrons can be shown like this. So this rho plus, and this corresponds to the psi minus, which is called rho minus. Okay. This rho plus concentrate the electron near this positive ion core, and rho minus takes this concentration away from this positive ion core. The potential energy of the rho plus is less than the potential energy of the traveling wave, whereas the potential energy of rho minus is greater than the potential energy of the traveling wave. There is an energy gap between this psi minus and psi plus. Okay, so this difference is called the energy gap. Okay, so at k equal to plus or minus pi by a, so there is an energy gap between these two wave functions. Okay, psi plus and psi minus. So that is called energy gap. This is about the nearly free electron model. In the next class, we will discuss the modification in the nearly free electron model, that is the chronic penny model, that will explain the band structure of crystals. Okay, see you.